Hello again, and welcome back to my computer vision series. Today we will be reading the code of the DINO model for object detection. In a previous video, we talked about the model itself and the algorithm. Today we will focus on the official implementation in PyTorch, and hopefully that helps answer a lot of questions that you may still have about the model. Before we start, just to understand what's going on today, you will need to know what PyTorch is, what transformers are. Also, the model itself is quite complex, and it is built up on top of a series of transformer-based models such as DETR, deformable DETR, DAB DETR, and denoising DETR. And actually have a series about all of these. And you can see if you just open the code for the very first one, the DETR one, it is really simple, it is really compact, and then every next model just keeps adding stuff to it and keeps making it more complicated. So if you get lost in the code in a more complicated model, I advise you to just return to the very first one, because it basically starts from the very beginning, and then you'd be able to trace all the advancements right in the code, and hopefully that will help you understand what's going on more. This is the plan for today. So we basically will go through the main parts of the model, at least what has changed as compared to previous models. So first of all, we'll go over MultiScale model input. So this is the main addition from deformable DETR. We will go through contrastive denoising training, and it is consisting of two parts. One is the query setup before we pass some information through the decoder. And the second part is loss, which is used during training. So what do we actually connect those queries to? Then we'll go through mixed query selection. That is, how do we get the information out of the encoder and use that to create better inputs for the decoder. And finally, the look forward twice scheme. So before we start, a quick couple of words about how to set it all up. So right now I am in the official repository for DINO model. It comes from IDEA Research. It has all the instructions on how to install. So you would need to just go through these. Basically, you would need an NVIDIA GPU and CUDA, because of this custom deformable attention layer that I believe is just copied from model to model. So it originated in deformable DETR, and it has been present in all the models since, which is a bit unfortunate compared to the model like YOLO, which runs on pretty much any device you can imagine. So mobile devices, embedded devices, CPUs, metal performance shaders from Apple, and so on. This one, you can only run it on NVIDIA GPU, which is, I guess, a huge limiting factor in the popularity of the model itself. Nevertheless, this is what we're talking about today. So basically, you need to clone the repo, set up a new environment with PyTorch using Conda, install the requirements, and then the final, most important part is this setup.py that will actually compile custom C++ CUDA layer, and then run some tests to make sure it actually works. Obviously, you would need to download the data. So object detection typically is trained on the Coco dataset, which is relatively small, just 20 GB. So you wouldn't have problems with downloading that to your laptop, for example, which is really cool. And finally, I have a template of Jupyter notebooks that I use to read models like this. So I'll provide one in the description, where we basically import the dependencies, define some useful functions like how to actually plot the images that we're about to pass through the model and the bounding boxes. All of that is really useful in understanding what is going on, because it's quite hard to argue about just tensors, but when you actually can see what we pass as an input, everything becomes more clear. So here's the example of the dataset. So the dataset is just the thing that basically loads images one at a time. And here it is with annotated classes and bounding boxes. This is the very first image in the Coco dataset, so we've seen it in a lot of videos already. If you just rerun this cell, we can get a sense of what sorts of data augmentations were used. So you can see that the image sort of shifts a little bit every time. Sometimes it flips left to right. So this basically means that we use a random resized crop. So we crop slightly different part of the image every time. and randomly flip it from time to time as well. So it is some data augmentation, but not as heavy as you might have seen in other big models like Swing Transformer, for example, that used a lot of color changing, a lot of shape shifting, and so on. This is quite lightweight, I would say. Then we have our data loader, and the data loader is the thing that actually pulls the images from dataset and then unites them into batches. So now if we come back to our dataset, over here, I'm just printing the shape of the first two images. And you can see that they are quite high resolution, but not like Ultra HD, and they all actually have different shape. And that's typically is a problem with tensors because typical layers prefer tensors to be of the same shape. So it is solved by the data loader by adding what we call padding, and you can see it in the bottom of the image here. So basically we have two images in a batch because batch size is 2, and they will most likely be of different sizes. So to compensate for that, we just pad them to the same size with zeros, which after unnormalization looks like this gray area here. So we use that as an input to the model. We pass that through the model itself, which basically means that the model sees this gray area in the backbone. But then we apply the special mask before passing that to the transformer so that the actual transformer attention ignores this area completely, as if it was not even in the image in the first place. Then we just basically build the model, and all of this code is pretty much copied from the main.py of the repo itself. There's not too much code here, and we'll read some of it today. So thanks to the fact that I've already loaded my batches through the data loader, I can actually just call the model and get out the outputs, which is really useful. This means that everything was installed correctly, and I can actually read the code of the model right now. And pretty much the rest of the video will be focused about debugging what is going on in this cell. You can also see that we are passing the targets to the model as well, and that happens because of the denoising loss. So to actually set up the input to the decoder, we have to pass the ground truth bounding boxes to the model as well, even during inference. But don't worry, that doesn't happen when you actually evaluate the model or use it in production. And finally, this is how we can calculate the loss, and we'll spend some time in the loss calculation as well. Now let's start actually reading the model code, and we'll start with the MultiScale model input. So first of all, here it is on the diagram I've shown above about the DINO, and maybe the more representative one from the formable DETR. So basically, we always start object detection by passing our image through the backbone. That backbone can be something like ResNet, where the image is passed through a series of layers made of convolutions. And after every layer, the pixel resolution is decreased, so the image becomes smaller, but the feature richness of every pixel is reduced. So we go from just raw pixels depicting colors in a specific location in RGB to simple concepts like gradients, edges, to corners, to more advanced objects like head of a dog or a specific letter, and so on. And if we look at transformer-based backbones like Swing Transformer, it is more or less the same. So we start with high resolution, raw, unprocessed image, and downsample it to lower resolution but higher feature richness. And processed version of the image is really good for classification. But then if you need pixel-wise predictions for the bounding box, for example, you still need that high resolution image to understand where exactly the object ends. And it's the main advancement of deformable DETR was to modify attention in the transformer in such a way that it's no longer quadratic in complexity, but linear, by basically saying that every point in the output now only attends to 4 points in the input. Thanks to that, it's now much simpler to pass giant high-resolution images through the transformer, But we still want this later, more processed version, because otherwise, why have backbone in the first place? So basically what we do is we take the lowest resolution, most processed version of the image, as well as the one before that, and maybe before that as well. So we get all of them at once, just concatenate them together, flatten them out, add some level positional embedding and position embedding to specify where the pixel is within the image, and just pass all of that information all at once through a transformer. So now let's get back to our code. First, I need to find where to put the breakpoint. Here is the code for constructing the model. Let me just quickly print what is the model name. DINO. So the code here is this build function. It's quite complicated, some registry where you can just define the model and find it for you. Thankfully, I already gone through that. So the model itself is defined at model/dino/dino.py. If we scroll down, we see this build DINO function, which indeed is defined within this registry under the name DINO. And basically, this function sets up the entire model as well as the loss. And the model is called DINO. So you can just go to definition. We can see that this is a typical PyTorch model that inherits from nn.module. And we just scroll down to the forward method and just put a breakpoint here. So now, thanks to the fact that I have my very useful notebook, Jupyter notebook, I can just find the cell where the model is actually applied, and then just call debug cell. And here I am. So I've stopped right at the breakpoint where I wanted to. Let me just confirm that what sorts of input I got. So I get an input as a nested tensor, which is the one with the image and the mask to basically ignore this gray area. So if I go to samples.tensors, that will give me the actual image part. And so I can see that I got two images, 3 colors each, and they got padded to the maximum dimension of 861 to 1007. So these are my two images. Then I pass that through the backbone. I get out the processed version as well as the positional embedding. And we can see here that features that we get out of the backbone has a type of list, and the length of that is 3. And the first element of the list is a tensor, which basically corresponds to the highest resolution processed version of the image that we got out of the backbone, similar for second and third objects in this list. So you can see that we started with 800 by 1000 pixels. The highest resolution feature map that we get within the model is roughly 100 by 100, and then another one 54 by 63, and another one 27 by 32. But then in this highest resolution one, we have 512 numbers per pixel, and then it goes up to 1024 and 2048. And that's not it. So you can see here. So here we set up the mask. Let me just scroll down here. We have this self.numFeatureLevels variable, which is equal to 4, which is basically saying that we want to have 4 different scales as inputs to the model, but the backbone only gives us 3. So we can actually just create another one by ourselves by just passing that through another convolution layer. And here is what happens here. So we have our input projection, which is basically this convolution layer, which, let me just confirm that. We can see the definition for that in the init method. And here we can see that it is conv2d and group normalization. Let me just confirm that over here as well. The type of this is module list that consists of a list of convolution group norm, convolution group norm, convolution group norm, convolution group norm. So it's a bunch of convolutions to project my already low resolution image down to even smaller resolution. So I can just iterate forward to here and see that now my SRCs, length of that is now 4. And so the final image within this sort, so the first one is still 100 by 100, and the fourth one is even smaller, it's now 14 by 16. So we basically created an extra fourth level because why not? And the very next thing in the code we see is this prepare for contrastive denoising loss. Okay, now let's have a reminder of what contrastive denoising training is. So first of all, here's the scheme of DINO overall again. So we've looked at this MultiScale input. I haven't really looked at that, but basically before flattening everything out and passing that through the transformer, we want to have positional embeddings to remember where each pixel was located. So all of that gets flattened out, then passed through the transformer encoder, which is basically just refining the inner representation of the image to understand better what that is. And then we have the decoder. So decoder receives this side input from the encoder as information, and then something from the bottom as query inputs. And the output of that is the actual predictions for what is there in the picture. And so in the white here, we have the original DETR predictions, where the output, which is basically embedding in each token, it gets projected down to bounding boxes and to classification prediction and connected to ground truth objects using bipartite matching loss. And bipartite matching loss is basically needed to solve this problem of which query output to match where, what happens if we have duplicates. So bipartite matching loss handles that really well. So in case of duplicates, it will just choose the best match from query outputs and match the one that is the best for this object. And then the second prediction, which is a duplicate, will get matched to the so-called no object class, thus penalizing the model for duplicates. But as we've seen in the previous videos, it is unstable. So this matching might change from epoch to epoch. And one big problem with that is that even if you as a query were really close to getting a good prediction, if you're not actually matched to the object, you get no positive feedback about how close you were. So this is basically saying that all bets are on just the best prediction. So if the best prediction is wrong, everyone else in the class was sort of left in the dark because they were not receiving positive feedback about how they might have potentially predicted something close enough. And because of that, the entire training is slower and the final result is worse. So what denoising loss does is that it just explicitly adds a special sort of queries that basically solve similar problem. So if normal white queries on the picture as formulated in the dynamic anchor boxes DETR, they consist of some content embedding and the positional embedding that is getting constructed out of just anchor boxes. And so for denoising loss, we have denoising queries where the content embedding and the anchor boxes, and the bounding box as an input, they get constructed directly from the ground truth. So we know the objects that really were in the image. We add some noise to them to make the task challenging for the model. And then we ask the same model to now solve this slightly different task of removing the noise from the class and from the bounding box. And this is auxiliary loss. It is not present in inference in any form, but it connects the query to the loss directly. So it has no this bipartite matching component. So it is completely stable and it helps speed up training. And now contrastive denoising loss is basically adding negatives to the scheme. So here you can see that's the bipartite matching loss. So we had 2 birds on an image. Our model predicted 3 birds, and so one of them had to be connected to no object. And then the model also predicted the phantom cat in the background, which is also penalized by connecting that to no object. Then here we have the normal denoising loss, where we had a noised version of the bird coming in as a query. The model denoises that and gets some approximation of the original bird, and then the loss says how good that approximation was. And then the second negative part is when we add even more noise. So we now get a really bad anchor, a really bad starting point to do some predictions. And we tell the model to connect that to no object, basically saying that, if you see the bad prior, just ignore it. And thus we teach the model to reject unlucky anchors. So now let's get back to the code. I'm just jumping straight to this prepare for CDN contrastive denoising loss function. Let me put the breakpoint here and see what happens. So first of all, we have this if condition here, so if training. So we are reading the inference code now, so it will work for training as well as for inference. But we have this condition that says that if I am actually doing the training and I know ground truth for this image, I will perform this setup for denoising queries. And if I don't, in the very end of this function, I'm just not doing anything. So the model will still work even if I don't have any extra queries added to the decoder. So now let's actually read the denoising setup. So first of all, we have a bunch of hyperparameters and the actual targets. So the targets here should contain ground truth objects for the 2 images that we have in our batch. So that includes labels and bounding boxes. And we can see that all the labels for the first image are 21s. I believe we've seen that image. There it is. So we have 4 cows. I believe 21 stands for a cow. And then for the second image, we have 2 labels, 70 and 81. So then we have this DN number and label noise ratio box noise scale, which basically control. So DN number is the number of denoising groups. So we have 4 ground truth objects. We'll have positive and negative version of that. So 8 in total. And we'll repeat that for every group. And we can see some complicated setup here, which basically aims to balance between too many denoising queries being there when we have a lot of ground truth objects on an image versus too few when we have just 1 or maybe no objects at all. So basically what that ends up doing is, in our case, the DN number will be 25. So we have 25 denoising groups. We can also compare that to denoising DETR, which only had like 5. So the total number of denoising queries also has increased in this model. Next, what we do here is we basically concatenate all the ground truth objects into a single tensor. Now the labels is just one tensor with all the 6 objects grouped together. We'll use that to set up our noised queries, and then we'll expand them back into 2 images again. And that's what this setup basically is about. So the next interesting part is here for setting up noised labels. So again, we know original labels, just 6 of them. And we can see here that they are already expanded into 300 denoising queries that we are setting up. So again, we had 25 groups, times 2, that's 50, so positive and negatives, times 6 objects that we had, that's 300. And these objects are just cow, 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 and then this 70 and 81, I'm not sure that is. So 6 different objects repeated 50 times. Then we decide randomly which of them to flip, and the ratio is 0.5, so we'll flip roughly half of them. We choose indices for that, and we've chosen 72 indices, so slightly less than half. Oh, actually, yeah, the label noise ratio is multiplied by 0.5, so we have selected roughly 25% of all indices to flip. And then we replace what we had originally with just random label from 0 to num classes. So now what we have now, we still majorly see 21s, 70, and 81, but then from time to time we can see that some of them are flipped to other random labels like 83, 80, 2, and so on. So we're basically adding 25% of noise to the original labels before creating this content representation. And then we'll do something similar for bounding boxes. So for bounding boxes, we select these positive and negative indices. So shape of this one is 150, and for this one is also 150. So out of 300 denoising queries that we are setting up right now, half of them will be positives to be connected with the actual ground truth bounding boxes, and half of them will be negatives to be connected to no object class. And then what we do here is we just set up different sorts of noise for positives and negatives. So here, rand sign is random int. So we'll get numbers, random numbers that can either be 1 or -1. And then we have this uniform noise. So the rand part is just a random tensor from 0 to 1. So this is our noise. Now what we do for negative indices is we add 1 to this noise. So for positives we had noise from 0 to 1, and so for negatives we'll have noise from 1 to 2. Basically twice as much noise. And that is the only difference in setup of denoising queries for positives and for negatives. So like most of the contrastive denoising loss is this line here, which just says, give twice as much noise to these sorts of queries. But of course there will be another small part in the actual loss on how to actually connect these queries to the loss later on. So then we multiply this part, which is always positive, by random sign to make sure that it sometimes is positive, sometimes negative, and then we actually add this multiplication of bounding boxes by this noise and box noise scale. So box noise scale is a hyperparameter that controls how much noise do we actually add. Then we do the clamp to make sure that the bounding boxes are still located within the image, and that concludes the denoising setup. So right now we started with original classes, original bounding boxes. We've created noised versions of them. We also need to create the actual query inputs. So for bounding boxes, that's just 4 numbers for x, y, height and width, and that's it. So we actually pass that to the decoder. For labels, we also need to project that down to embedding, to the content embedding. And we do that using this label encoding. So the type of label encoding is sparse embedding. So it's just embedding matrix, a trainable matrix of parameters. And the shape of that is, shape of that is 92 by 256. So 256 is our hidden size of everything in our transformer, and we have 92 classes. So we do these projections, then we do this operation of taking 300 queries. 200 of them belonged to the first image and 100 belong to the second image. Then we need to expand that back into 2 images. But since they are now of different length, we also want to pad the smaller one. So we'll have size of 200 for both of them. So the padding size here is 200, I believe, right? So basically the first image will just have 200 queries, and the second image had just 100 queries, and another 100 will be added as just padding. And this is basically what we output. And everything else, I believe, in this. So let's see. So input query label is the actual content embedding that will be used later. The shape of that is now 2 by 200 by 256. So we split the common sequence of 300 queries for both of the images, separated that into images, padding one of those. And let's look at the second image. And we can see that the padding is just zeros. And then for bounding boxes, again, we pad with zeros, basically. So you can see that we had two objects, here they are, and then two padding boxes. We also have the attention mask here. So the purpose of the attention mask is to not allow different denoising groups to attend to each other, because they have slightly different noised versions of ground truth objects. And just by looking at ground truth objects with different added noise 25 times, you might get a pretty good idea of what the original object was. So we disallow that. We only allow denoising group to attend to other objects within the group. And the same goes for the actual real queries that are being passed through bipartite matching loss. So they also are not allowed to attend to denoising queries, because there will be no denoising queries during inference. So we don't want the model to learn to rely on that. So here's how we set up the attention mask. And we return these query labels, query bounding boxes, attention mask, and DN meta is just some extra information like number of denoising groups that we had and the padding size. So let me just quickly scroll to that, and just a quick reminder of all the shapes that we had. So basically we've created 200 queries, 200 content embeddings, 200 bounding boxes, which comes from 4 objects that we had in the first image, and in the second image we just had 2, so we padded that to 4 as well. Then 25 denoising groups, which is a hyperparameter, but it is adjusted slightly based on how many ground truth objects we have, and we multiply that by 2 as well to have positives and negatives. Now, after preparing for the denoiser loss, we basically have these denoising queries, and we'll pass them to the transformer. So this transformer call basically does everything else. So it has decoder, it has encoder, it has decoder. The output of that is basically the predictions of the model. So before we read further, let's break here and look at the loss for a little bit. So we can find it down here when we've set up the model. So here was the definition for the DINO, and the same function returns model and criterion as well, and the criterion is the loss. So let's go here. Again, it's kind of like an Android module, so you can scroll down to the forward method and just put a breakpoint there. But to actually get in there, we need to calculate the loss. So now we've applied the model, we've got our predictions. Now we need to apply this criterion, and I just press debug cell here, and I should get into the actual loss calculation. And here I am. Now let's print a little bit, like what do we have here. So outputs here corresponds to everything that the model predicted. So for example, pred logits correspond to the output of every query and the logit for every possible class. And the shape of that is 2 by 900 by 91. So this is the real prediction of the model, not the denoising auxiliary prediction. Auxiliary prediction, I believe, is hidden somewhere in the in the outputs. So outputs without auxiliary stands for real outputs, and we have 900 of them, and everything else should be auxiliary, and there should be 200 of them. Right. So almost the first thing that we do here is we pass it through the matcher, and the matcher is precisely this bipartite matching loss that actually matches these 900 queries to one of the ground truth objects. We'll not look into that in detail. I believe we did it in the original DETR video, but let us just look at the result of this. So as a result, we get indices, and they basically contain, so we have indices is an object of length 2, so we have 2 images in the batch. We have indices, which is an object of length 2. The first one contains 4 indices corresponding to which query outputs got matched to that, and the second part here stands for what they got matched to. So we have 4 ground truth objects, and then this query got matched to the index number 0, this query got matched to index number 3, and so on. And then the second image only had 2 ground truth objects, so we only have 2 in the second part. Then we can just quickly search to see where these indices are used, and we will see that they are mainly used in this get loss call. So the get loss call basically calculates the loss of everything. So it has the logits outputs of the model and indices, what turned out to be the ground truth classes for all the predictions, and then it compares them and calculates the loss. But that's for normal queries. So the part that will be there during inference, not including the denoising part. So we can see the denoising part somewhere here. Let's just scroll here. So basically, we've passed the denoising outputs as well as part of the outputs dictionary. And here we basically reconstruct which ones of them were positives, which ones of them were negatives. So we do that because we basically know which indices were constructed as positives, which were constructed as negatives. And then if we actually search for this negative IDX, we don't really see any uses of that. So it's not really passed anywhere else. The only thing that is used is this positive index, and it is used in the same way as the index from bipartite matching loss. It is just passed to the get loss method that basically sees these ground truth classes and decides how to compute loss based on that. The logic behind that is that everything that is not positive implicitly is treated as no object class, which is just what we wanted. So now let's read this get loss method. So it basically has a bunch of losses, labels, cardinalities, just auxiliary, I believe, boxes, and masks, and I'm not sure what is, to be honest. But let's read just one of them. Let's read the one for labels. So let's break here, continue, and just print what we have. So indices.shape. Right, so indices is again an object of length 2, and the first image has 100 ground truth objects in here. So we can say that this part is for denoising loss calculation, and then the second image has only 50. So actually, our original image had only 4 ground truth objects, but then we have 25 denoising groups, so we got 100 in total. Then we have our indices, which basically come from the positive indices that we remember to be positives when we constructed the denoising queries. Then we have this target classes original. Let's just print that. And we can see that it's 21, 21, 21, 21, 21, 21. So all our cows here, and then in the end, objects from the second image, so 70 and 81. And then we do this target class, which is constructed as torch.full from src logits shape and self.num classes. So self.num classes is the number of classes in the Coco dataset. And we basically construct this tensor from 91s, right? And 91 in this case stands for no object. So basically we say that the first number of classes elements correspond to some real objects that might actually be there. And then the final one, the 91 index, stands for no object. So we constructed target classes tensor as containing only no object classes. And then we fill that in with the specified indices. So some of them are now matched with the original stuff that we had. So cow, 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 and then a bunch of objects for no object. So this is how we implicitly connect those negatives that we've got from prediction to the no object class. And we can also see the pattern, like how exactly positives and negatives were constructed. So we had 4 objects in the original image. So we have 4 positives and then 4 negatives. And again, 4 positives and 4 negatives. So these are the ground truth classes. Then we turn that into one hot, and then we have this sigmoid focal loss, which basically feeds in the src logits, which is just a tensor, 2 by 200 by 91. So this is how we basically connect the prediction of the model, where each of the 200 denoising queries predicted probability for one of the 91 classes. And we connect that to the ground truth, which for positives was the actual ground truth objects, and for negative, it was just no object class. Now let's look at what is called mixed query selection. So I'm back to my code. The last time we were reading the inference code of the model, we stopped at the prepare for CDN function. So let me just break right there once again and debug model inference. And here we are. So let me just step through that. So the prepare for CDN function prepares the denoising queries, the 200 of them. And the very next line here is this transformer call. So let's put some interesting breakpoints. So transformer is initialized before this DINO model. So yeah, at the bottom of this file, we can see that the DINO model is constructed and the transformer is passed from the outside. Let me go to the definition here, and it basically returns this deformable transformer class. So again, this one inherits from nn.module. So let me scroll back to forward method, put a breakpoint here, and let's see what happens. Right, so first of all, inputs and some setup. So type of this is list, length of that is 4, so this stands for 4 different resolution scales that we pass in. Then we have a bunch of code that originated in the deformable DETR. So basically have this 4 input scales, each of them a 2D image. So we are about to just flatten all of them out and just concatenating them into one giant sequence. And to make sure that we keep the information about which point or at what position within the image and to what scale it belonged to, we also have positional embedding and level position embedding. So I've been through that in my deformable DETR video, so here we're just going to skip through this somewhere here, but I'll just bring the shapes of what we have so far. So now src flatten is just one giant sequence of 18,000 elements. So it's quite big, but deformable attention is quite lightweight, so it's able to process that. So a lot of interesting stuff is happening in the decoder, the actual deformable attention itself. Again, we've looked at that at deformable DETR video, so I'm just skipping through that. And now we have some interesting stuff. So now let's come back to the presentation. So what exactly was meant by mixed query selection? So we've just passed out of the encoder, basically creating refined representation of the image. So the shape of the output is the same shape as the input. So basically what we get out is this flattened pixels that still correspond to some locations in the image. And then we have the decoder. And so in some previous models, the input to the decoder was initialized completely statically. So you'd have static content embeddings that are just trainable, and you'd have anchors that basically correspond to some priors to where the objects might be and what size the objects might be. Here we do what is called mixed query selection. So we still initialize the content embedding as just a trainable matrix of parameters independent on the actual image content. But anchors actually come from encoder output. So encoder output is the sequence of tokens, and each token is basically an embedding of size 256. Now, what we are going to do is we're going to project that to class output and bounding boxes, and then we'll select top 900 by the probability of the class. So you basically use this class projector to decide which tokens seem to have detected an object with highest probability. And then we use bounding box projector for the same token to come up with actual query initialization. And this is it in the code. So first of all, a little lesson on reading really complicated code that might be too complex for you to understand from the very first try. So here I have my memory. So memory is the outputs of the encoder, and we can just print the shape of that, still this giant sequence. Then we pass that through the function again encoder output proposals. You might be cheated into thinking that this is where the actual proposals are being formulated. Let me just quickly go to the definition of that one. And so we know that we need to apply the projector to the memory somehow. But here, what we are actually doing is we only use memory shape and memory padding mask. So we are not really using the memory content as such. We also have this spatial shapes tensor, which is just basically original resolutions of all the 4 scales that we had. And we also have a lot of geometry here. So grid, mesh grid, scale, and so on. So I'm not really going to read that. Instead, I'm just iterating through this, and let's just print the shape of what we've got. So it's 2 by sequence length by 4. So 4 is supposed to stand for x, y, height, and width of the actual bounding box. So we get something for every sequence element. And let me try to print what we've got. Let's say for the 100 to 300, right? So what happens here? And we can see some pattern, right? So height and width are always the same, mostly. And they seem to be just increasing. And then what happens to these output proposals on line number 304 and 40, is that we have our output memory. We pass that through self.encoding output bounding box embed, and the type of that is MLP. So this is the actual multi-layer response. This is our actual bounding box projector. And then we add that to output proposals. So what actually happens here is the actual proposal generation happens here, where we take output memory, so the encoder output basically, pass every token through this bounding box embedding, and get some sort of bounding box prediction out. But this bounding box prediction is what we call relative. So it just says that, whatever object I'm detecting is going to be like 3 pixels up from me and 2 pixels to the left, for example. But in the loss, in the output of the model itself, we always deal in absolutes. So the actual bounding box that we see in the loss, the bounding box that we pass in as a decoder input, they are always in the terms of the absolute coordinates within the image. So the bounding box that starts at pixel 100 on the X scale and pixel 990 on the Y scale. So to convert this relative bounding box prediction that comes from the encoder to this absolute one, we basically add this output proposals offset, which is generated knowing the original geometry. So remember, in this 18,000 sequence length, every token still corresponds to a specific point on a specific image, on a specific level. And we basically can decode that out, knowing the initial spatial shapes, and convert that to the actual offset that we want for our bounding boxes. And this is what happens here. So let me just quickly go through that. And here's how we generate our output proposals. So we generate proposals for the class and for the coordinates. And both of them have the same shape. And the shape of that is basically this sequence length here. So for class, we have 91 class predictions. For bounding box, we have 4 bounding box coordinates. And then what we do is we select top k of them based on this class prediction. So basically, we're saying that we have 18,000 tokens. We let each of them predict 91 numbers for probabilities of each specific class. We select max of that, basically saying, what is the highest probability for some class that you've predicted. And then we select top 900 of them as our selected queries. Yep, so top k is 900. So in the decoder, we'll have 900 normal queries and 200 denoising queries. So this top k proposals are just indices. So we had roughly 18k tokens, and each of these indices basically say which of them were selected. And then we just basically gather the actual class predictions and bounding box predictions using these indices. Right, so we'll talk about this undetached name in a little bit. For now, so we have this ref point embedding selected, which is basically bounding boxes. We try to do the same with target, which is the same thing but for content. But here we have this flag called self init target, which is true, which is basically saying that instead of using this proposed content, proposed class predictions, we actually want to just initialize that ourselves using this static target embed. The type of this is sparse embedding. So basically we're saying that we are going to ignore what is actually happening in the image and just initialize the content embedding statically. And this is the principle of mixed query selection. So if we just would initialize that from the encoder as well, that would be just query selection. And mixed query selection is when bounding boxes are initialized dynamically and class content embeddings are initialized statically. Right. So, and then after this, we basically have this ref point embed, which is the concatenation of this ref point embed with the underscore, which we just initialized using encoder proposals, and this ref point embed without the underscore, which we got as an input, and that is basically the denoising queries, denoising bounding boxes that we got as an input. So we then concatenate them all together, and we pass that through the actual decoder. So before we dive into the decoder itself, let's also briefly discuss this undetached thingy here. So basically here in the code, we have this projector that is called bounding box projector, class projector. We can call it whatever we want. It will not actually work as bounding box projector or class projector until we connect it to the loss, right? And none of this will work before we actually connect it to the loss, because the predictions are just random, and they don't mean anything. So in order for them to mean anything, we need to connect that to the loss somehow. But the main stuff is going to be happening in the decoder. Thankfully, we have what we call intermediate losses, where each intermediate output of the decoder layer, including the input itself, is also connected to the loss. So before we even started decoding stuff, we have our class outputs and bounding box outputs from the encoder that we just got, and we want to feed that in as an auxiliary loss to make sure that we also train this encoder, we train these projectors in such a way as to actually predict real bounding boxes and real class embeddings. So this undetached version of ref point embed, for example, is going to be just returned from this function here. So here we basically say this target undetached, ref point embed undetached to this HS encoding and ref encoding, and that is returned from our transformer function. So this is what will connect to the loss later. And then the detached version, this one, is going to be fed into the decoder. So here we see some concepts from the next point, from look forward twice, where we don't actually let gradients to flow all the way through all the aspects of the model. So for things like bounding boxes that control the attention modulation and so on, we try to keep the gradient flow limited to just 1 or 2 layers. And that's why we have this detach here. So this undetached version is only connected to the loss, but what is actually fed into the encoder, to the decoder, is detached. So the gradient doesn't flow from this attention modulation mechanism backwards to the encoder, to the projection heads, and all the way to the beginning of the model. And that is basically helping stabilize the training. Okay, so last we want to look at the decoder itself and the look forward twice scheme. So I'm coming back to the code. Let me just show you that nothing interesting really happens before the decoder. So here we concatenate our denoising queries with the queries that we've just got out of encoder, and then we call our decoder. So let me just find it. Decoder, there it is. Again, this is just an end.module. Let's scroll back to the forward method, press continue. So a lot of stuff that is happening here is coming from DETR. Again, I have a video about that, so I will not stop on all of them right now. Let me just explain the inputs at least. So memory has a shape of sequence length by batch size by hidden dimension. This is encoder output, as is. The target is the content embedding input to the decoder, and in our case, it's statically initialized. So we have, by now we have 1,100 input queries, so 900 from real input queries that try to predict objects in the picture, 200 from the denoising inputs, and then the batch size, hidden dimensions are the same. Then we have this ref points on sigmoid, which represent the bounding box input to the decoder. And the shape of that is again 1,100 by 2 by 4. So then what happens? So we have this reference points that we take out of this unsigmoid version by taking the sigmoid. We're going to save that to this ref points array, basically to return all the intermediate bounding box inputs that we have as input to every decoder layer, including the very first one. And that will be connected to the loss. And then here we see a lot of code of setting up the actual decoder layer input. So these bounding box inputs, apart from just being an input to the decoder, they're also used to perform attention modulation. So modulation of position of attention that will be performing within the decoder, as well as the size of the attention. So we're not going to stop on that. And this is basically what is happening here. So first we get the sign embed. This is how we project 4 numbers to the hidden dimension that we need, 256. Here we have modulated attention, modulated height and width, and so on and so forth. Then we call the actual layer. So the layer here is the decoder layer, so self-attention, cross-attention, all of that stuff. And the output is basically the next iteration. And then we perform what is called the iterable update. So let me just scroll right to that one. So we had our reference points, and now we have our model prediction, the layer prediction. And basically, input bounding box is like a prior to where the object might be. The layer tries to correct that, tries to predict some offsets, and basically shift this bounding box approximation. So to actually get this delta bounding box, we also project the layer output. So we have this output, which came from the layer, from the decoder layer. We have this bounding box embed. Let's just validate the type of that. That's just a module. 6 MLP classes, right? So again, just a bunch of dense layers. Although, yeah, there are 6 of them simply because we have 6 layers. So we're actually using just one dense layer in every specific case. So we project that to the actual bounding boxes. We add them up, get new approximation of the bounding boxes, and that's how we get new reference points, basically. And then what we do is we basically want to update the input to the next layer. Let's see where that happens. So we are going to set up input to the next layer, the reference points to the new reference points. And then depending on if we do look forward once or look forward twice, we have to detach the gradients differently. So in our case, new reference points are going to be initialized with the detached gradients, but then the output will use these new reference points, which basically means that these new reference points that we just got that are basically containing initial reference points plus the delta predicted in the specific layers. This is the one that we pass outside of the model and connect to the loss, thus ensuring that this initial bounding box approximation was used in basically 2 layers at the same time. So the original approximation for the bounding boxes and then the corrected version of that. And this is the look forward twice scheme. And that basically concludes what's happening in the model. So we return from here, we connect these 6 layer outputs to the loss, and this is pretty much it. So this concludes the video about reading the code for DINO. I hope that my explanations were clear enough and actually reading the code helped you clarify some things. I want to take a moment to just describe what else I have on my channel and what I'm planning to do next. So today we're talking about reading source code for DINO. Apart from that, I also have videos about a lot of other object detection models, starting from YOLO, DETR, and variations of that build up to the DINO itself. So deformable DETR, DAB DETR, denoising DETR, all of the most famous backbones, ResNet, VIT, Swing Transformer, and I also started a series about NLP, and I have the first video out about reading the source code for GPT-2. The very next video I want to make about reading the source code for BERT, and all that actually leads up to a really cool model that I was planning to do for some time called Grounding DINO, which is a really cool zero-shot multimodality model that is basically trained on text and image at the same time, which in turn allows it to do what is called open set object detection, where instead of relying on 90 classes from the original COCO dataset, which in many cases is very restrictive, it can actually predict things that were not explicitly defined as a class, but just instead described in text. And in addition, it's a really cool concept, I believe, similar to what is used in a lot of other foundational models like GPT-4, for example, that lets it basically understand text and image at the same time and perform this cross-attention between text and image. So we'll see all that in action. I also want to make a video about the current state-of-the-art system called DETR, which basically overtook the DINO, but all the main concepts are still the same. They come from DETR. So we have a lot to cover. See you soon.